So thank you to organizers for an opportunity to give a talk during this conference. This is a double pleasure for me because I am a former student of this institute, of this university. And today I'm going to present you the method of coupling matter field to gravitational field in the framework of loop quantum gravity. Let me first present you such example. We can imagine a particle that, if it is excited to very high level of energy, if the energy will go to infinity, we have problem in quantum field theory. Theory is divergent. However, we know from general relativity that before it happens, the particle falls into its own black hole. And this is the regime when quantum gravity works. And in the framework of loop quantum gravity, we know how to do it, how to describe the such situation to get convergent formulas. We can do it in the following way. If we have some dynamical operator squared that describes this particle, we can try to smear it, introducing this smearing function of a box of volume epsilon cube that gives us convergent formula. However, it breaks the diffeomorphism invariance, and to recover it back, we can use next methods of loop quantum gravity that allows us to change this epsilon cube into some function of volume operator. And how to do it precisely, I will show you on a simple example of scalar field coupled to Einstein-Hilbert action in a framework of quantum reduced loop gravity theory invented by Francesco Cianfrani and Emanuele Alessi that are present here. For such theory, gravitational field is coupled to matter through dry-bind, or so-called cotriad. So I'm working now in 3+1 decomposition. And because in loop quantum gravity we regularize Hamiltonian on a lattice, we have to find some representation for a scalar field also on a lattice. So in this case we choose so-called polymer representation or point holonomy representation, where scalar field is placed at nodes of a lattice. Since I'm going to describe regularization via quantum reduced loop gravity, this lattice for that theory is a cuboidal lattice, so we can imagine a lattice that has 3 perpendicular axes. I will tell you a few words more in a moment. For such space diffeomorphism, for such representation diffeomorphism act naturally as unitary operators. And what we have to do, we have to find a way how to quantize second part, in this case, second part of Hamiltonian constraint, since the first one defines us diffeomorphism on a spatial hypersurface. The second one contains dynamics, and the second one must be quantized. Before I will show you how to regularize it and quantize it, I will define briefly kinematical Hilbert space for a theory. So the total Hilbert space is a tensor product between the one for general relativity for in loop quantum gravity and the one for scalar field. This superscript R tells us that I have in my mind quantum reduced loop gravity. It means that regularization is done on a cuboidal lattice. So the second one, Hilbert space for a scalar field, is defined in the following way: A and psi are coefficients, and the basic operators is the exponentiate sum of field attached to each vertex of a lattice. with some coefficients. We have measure in that theory that is Bohr measure. Here is compactification. This means compactification of a real line. And basic variables acts as follows. So maybe here it will be more clear if I take into account just single point states. So I have only one vertex, and this field is described as an exponentiate field attached to this vertex times some coefficient. Operators in this description acts the field operator as a multiplication and the momentum operator in Schrödinger representation as a derivative. We have well-defined Poisson structure for the theory, and we can try to quantize it. So this is Hamiltonian constraint that I divided into 3 parts, and we have to first regularize each part, and then we can promote functions into operators using methods of loop quantum gravity. So in loop quantum gravity, we use quantization during few steps. We have to implement so-called Tiemann's method, Tiemann trick, changing co-triads or drybines into Poisson bracket between Ashtekar SU2 holonomy, Ashtekar SU2 connection and volume. And if we want to regularize the formula on a lattice, we have to change Ashtekar connections into holonomies, SU2 holonomies. Then, okay, we get very complicated formula. However, we can check that for each part of the Hamiltonian we get convergent expression. Okay, it looks quite complicated. Let me just mention that the problem in calculation is to calculate such terms and to promote each field function into some function described on a discrete space-time, on a lattice. So we also expand derivatives in a proper way. The method of quantization in loop quantum gravity, and the same for quantum reduced loop gravity, is the following. So we have to promote Poisson brackets into commutators and volumes and holonomies into operators. So in the case of the first term of the kinetic part of Hamiltonian constraint, we get such expression, and the problem in calculation is the problem of action of this term on a state. We can do it now using the method of quantum reduced loop gravity. This theory is a theory that is a theory that sorry in quantum reduced loop gravity was invented to describe cosmology, and it differs from the quantum cosmology in this way that in quantum cosmology we quantize so-called mini superspace that was described in the previous talk. However, in quantum reduced loop gravity we first quantize full sector of general relativity and then perform the reduction. So we learn from the quantum reduced loop gravity that in the basis that diagonalize group elements, holonomies have very simple form with Kronecker delta, and we can apply this result directly to the trace of our operators, obtaining such formula where this sigma is the sum of quantum numbers that are attached to links in of the lattice that is used for regularization. And this, okay, here are some indices. This lower indices denotes the starting point of each link where this quantum number is denoted, is attached, and the upper one describes direction of each link. So I get the result. Okay, I introduce another function to simplify the formula. So this calculation is the result of such calculation is the following. So we have eigen states of each of such traces that can be put into the Hamiltonian, and as a result we get the following formula that looks quite complicated, and if you are not specialist in loop quantum gravity it looks maybe like a mess. However, we can see that the first part is the part that I called at the beginning kinetic part, the second part is derivative part, and here we have potential part. Here in these functions are encoded these quantum numbers attached to links that describes gravitational excitations. But what we get? We get convergent eigenvalue of the operator, well-defined analytic. So maybe we can learn something from it. And to do it, let me perform the following expansion for j, this quantum number, much bigger than 1/2. What does it mean? If we go with j to infinity, we should get flat spacetime. So this means this expansion. And in the first order of such expansion, we get formula that looks much familiar for us. Here I use the eigenvalue of volume operator and momentum operator. The last part that we have to do to get some information and to be able to perform phenomenology from such result, we have to deal with the matrix elements of discrete version of derivatives operators, and the same with the potential. We can do it in the following way. We use the characteristic function, and we change quantum numbers into gravitational momenta. In this case, if we replace directly matrix elements by its classical equivalence for continuous, its classical continuous equivalence, then we get known result. It means exactly Hamiltonian constraint for a scalar field in diagonal gauge. In diagonal gauge, so in the case when one can apply methods of quantum reduced loop gravity. It means that we started from the theory that can describe some cosmological model, and we found that in zero order in the expansion up to leading term, we get exactly classical expression. Next to the leading terms can give us quantum corrections to this expression. So let me conclude what we can do with such result. We can study phenomenological application using the next to the leading order results. We can use scalar field as a clock field. We can try to repeat the same calculation for fermions or vector fields. However, in my mind, the biggest achievements of these calculations is the proof that we can find some way to construct Hamiltonian constraint that has analytical matrix elements. So we are able to couple really matter field to general relativity and get pure quantum gravitational corrections that can be tested in cosmological model or in every model where we can apply methods of quantum reduced loop gravity. So in every model, when the matrix, when the metric is a diagonal. So thank you. Thank you.